This is section 1. And now we go to section 2, now we go to section 3. Now, section 2 talks about the force. Why? Because Newton's second law says that if there is an acceleration, object should absolutely act at a force, because acceleration is caused by a force. If an object is moving on a circular path at constant tangential speed, so what does it mean? AT is 0, but direction is continuously changing. There's AC, there's an acceleration, AC. Continuously changing direction produces AC. As I said, every acceleration is because of some net force. So this net force is named as centripetal force. It will have in the same direction of the centripetal acceleration according to Newton's second law. What does Newton's second law say that? F is equal to m times a. If there's a centripetal acceleration, it's a vector. So centripetal force must have in the same direction of centripetal acceleration and towards the center of the circle. So angle between FC and AC is 0. FC and AC, they are in the same direction. But the angle between FC and AT or VT, 90. Angle between, in short, angle between centripetal and centripetal component is 0. Tangential and centripetal components are 90 degrees. Okay, this centripetal force, any type of force which can keep an object in a circular path. For example, gravitational force. What does it do? Keeps the planets around the sun, keeping them in a circular path. Or the tension force in the rope. Tension force keeps an object in a circular path. Or electric force keeps electrons in circular path around the nucleus. Any force. It can be any type of force. Now, centripetal force is not a type of force. Any type of force which provides circular motion, named as centripetal force. And this force can be a single force, or it can be resultant of more than one forces. And why? Because sometimes two forces can act on an object. If there are two forces, you should find the resultant. That resultant force is going to be named as centripetal force. So this is the definition. It is defined as resultant effective force on a body. That body must move in a circular path, and again directed to the center of the circular path. Effective means, what does effective mean? We will talk about later. And magnitude of this force can be found out by applying Newton's second law. This is what Newton's second law. M times AC is equal to F. You can write AC in different forms. And you can write this equation in two different forms. One of them is mv square root r, the other is mr omega square. Okay. Yeah, we can solve this problem, but just be careful about this problem. This problem is crucial only because of that. The rest of them is M is given, FC is given, VT is the question. But this 3.25 kilometer circular track is not radius. Be careful about this. This is the length of the circle. Now, this is what sometimes we see is down. So 3.25 kilometer circular track is circumference. So you should first write 3 to 50, you should convert it to meter. After that, calculate the radius by using the circumference equation. 3 to 50 is equal to 2 pi r. 2 pi, which is 6.20 r. You should first get r. After that, you should start calculating. Okay, be careful about this. The rest of them is, you can do it on your own. Okay. Definition of the centripetal force is the resultant effective force on a body that moves in a circular path. I will make this definition a bit into components. I'm going to like one. Any type of force or any component of this force which lies along the radius is a part of centripetal force. Yeah, you should check the force if force is lying along the radius or not. To be what? Yeah, if a force is perpendicular to radius, this force is not effective. That's why they put in the definition effective as a word. Look at this one. F1. Is F1 is lying along the radius?
Yes.
Yes, it is. F1 is effective. So it's going to be centripetal force in here. Like what? Tension. And you move a object in a circular path by attaching a rope, a string. So tension is providing centripetal force, acting like this, along the rope, tension. So pointing the center of the circle, effective one. But sometimes more than one force can act on an object. We are going to see this case in an example. If two forces are acting on the object, this time we should apply definition, resultant. How can I find resultant? F1 plus F2 is going to be resultant. This is resultant. The definition of this resultant is what called centripetal force F1 plus F2 in here. But what if one of the forces away from the center, but still effective? So in this case, we are going to minus the force which is away from the center. Yeah, towards the center, positive. Away from the center, negative. So this is what is resultant of this tree? F1 plus F2 minus F2. This is resultant, and that resultant is going to be centripetal force. But if one of the forces acting perpendicular to radius, in this case, it is going to be ineffective. Yani, according to this definition, F4 cannot be included in centripetal force equation. Only F1 positive, F2 positive, F3 negative will be included in centripetal force equation. Then centripetal force is going to be F1 plus F2 minus F3. And what is F4? Tangential force. What does tangential force do? It produces tangential acceleration, which in your book it's not studied. Centripetal force produces centripetal acceleration. A tangential force, if a force acts tangentially, it produces tangential acceleration. Now, if somebody thinks that, what is the function of this force? This force causes AT. Can speed up or slow down object in a circle. That causes AT. Okay. What if force is acting inclined? In this case, you should resolve the force into components. This force has two components, X and Y. One component is effective, one of them is not. Which one is not effective? F1Y is not effective because it's acting perpendicular to this. Only effective one is a F1X. F1X is going to be the centripetal force. And example. A girl at a state fair swings a ball in vertical circle at the end of the string. Is the force applied by the string is greater than weight of the ball at the bottom of the ball's path? Here is the bottom of the ball's path. Let's draw the forces acting on the ball. Two forces are acting on the ball. One of them is Fg. The other one is Ft. Ft always acts along the rope. What is the direction of the rope? In here?
Upward.
Up. So you should draw Ft upward. Which one is greater? Of course, the one which is pointing to the center is greater. Which one is pointing to the center?
Ft.
So Ft should be greater than Ft. And also you can go this way. Resultant force is the centripetal force. What is the direction of the centripetal force? Towards the center. If it is towards the center, resultant must be towards the center. Resultant is always in the same direction of the greater component. Greater component is Ft, smaller component is Ft. At that position, Ft is greater than Fg. Okay, write centripetal force in here. Write how much is the resultant. Of course, you should subtract that. Positive and negative. Now, this negative and positive is not about positive or negative. It's about towards center, away from the center. So, how much is this resultant in this case? Ft minus Fg. You can write Ft, transfer Fg on the side. Ft becomes Fc plus Fg. You can write that. Then, let's think another position. When this ball comes in here, to the top of the, in this case, when the ball comes in here, rope is this way. Again, same two forces acting on the ball. Fg never changes direction. Ft towards the along the rope, right? But this time both are towards the center. Both are positive now. be at that position. Resultant is going to be Ft plus Ft. So this resultant is called what? Centripetal force. Write Ft equation. Ft is going to be Fc minus Fg at that position. In here you cannot make a comparison because these are not in opposite direction. To compare them, they must be opposite in direction. Which one is greater, which one is smaller depends on speed. That's why we cannot make a comparison. And one more position we will study. This position. What if this ball comes in here, right here? This is the rope. Fg never changes direction towards the center. Ft always along the rope, but this time rope direction is to the right. So now, which one is not effective? Fg is not effective. Why? Because Fg at that position is perpendicular to radius. Only effective force in here now, Ft. Yani at that position, Ft is only effective force, yani only centripetal force in here is traction force. And roller coaster example. A roller coaster car speeds down a hill past point A and goes up and past point B as shown in the figure. This figure is given. The car has a speed of 20 meters per second at point A. If the resultant force of the car is 2.06 times 10 to the power 4 at point A, right here, what is the mass? First, at point A, right here, resultant is given. In fact, what is given? Centripetal force. Because resultant effective force in a circular band is named as centripetal force. What is the direction of the centripetal force at that position? Towards the center. Where's the center? Yes, the centripetal force must be upward. Yeah, how much is the centripetal force at that position? 2.06 times 10 to the power of 4 Newton. So tangential speed is given at that position. It is 20 meters per second. So calculate the mass. Radius is also given. By using the equation, we can use the calculator. Because Fc is equal to m Vt squared over, because m is the question, transfer Vt squared over other side by r over Vt squared, m is going to be Fc times r over Vt squared. Fc is given, r is given, Vt is given, you are going to find how much it was 550. But besides this, I'm going to talk about this one. Yes, at that position, I know that Fc is the resultant effective forces towards the center and upward direction. But normally this force, centripetal force, because of two forces again. Two forces acting on the car at that position. What are these two forces? One of them is gravitational force. What is the direction of the gravitational force? Downward. Fg. Second force, normal force, because this car is in contact with the truck. Truck at that position instantaneous horizontal, normal force must be vertical, yani upward direction. Normal force is positive because pointing the center. Fg is negative because away from the center. Which force is greater in here? Fm. Fm. So always the force pointing the center is greater. Demek we should know that at position A, Fm is greater than Fg. Write Fc equation. Resultant of this what? Fm minus Fg is centripetal force. If Fn should be calculated, can be calculated? Why not? Fn is equal to Fc plus okay. Fc given. If mass is given, can we calculate Fg too? Yes. Fc is given, and if mass is given, you can calculate Fg. Also, when you edit them, you will find how much Fn acts on the car at that position. Okay, but after moving this position, this car goes to position B. Again, at position B, two forces act on the car. One of them is Fg, always downward. The other one is Fn is perpendicular to contact surface. Again, pull the same two forces, but this time their values are different. Because one of them is pointing center is positive. Which one is positive now?
FG.
Fg pointing center. But in here, Fn was positive, but in here, Fg is positive. Fn is negative. So which one is greater than?
FG.
Fg is greater. The one which is pointing the center always greater. At that position, opposite of this, Fg is greater than Fn. Write the resultant, in this case, Fg minus Fn is going to be resultant. Yani centripetal force is going to be at that position what? Fg minus Fn. So then you can calculate Fn by transferring Fc other side, you can write equations. But about this part, there is a question. Next part B is about this. It says that what maximum speed the car must have at that position for gravitational force hold the car on the track. What does this mean? At this maximum speed at that position, the track is about to leave, the car is about to leave the track. Yeah, it is moving on the curve but not pushing the track, which means contact is almost zero. If contact is almost zero, Fn should be, in this case, Fg is going to be Fc only. This is what the question tells you that. Yeah, when at that position only we are talking about, not in here. In here, no maximum speed. In here, we can move the car as fast as possibly we want. But right here, at the top of the track, if a car should follow the curve, follow the path, it can have a maximum speed, no more than greater than that. At that speed, Fn is going to be 0, Fc is going to be only Fg. Part B of this question is talking about that. It says that, what is the maximum speed the car can have at point B for gravitational force to hold the car on the track? What is the reason for this? Because at that position, as I said, Fg is Fn, Fg positive, Fn is negative. So Fg minus Fn is centripetal force. When speed becomes maximum, car becomes over the track but not touching the track. That's why Fn becomes 0. Only centripetal force is gravitational force for this statement said in the question. Fc is the only centripetal force. The rest of them, you are going to write the equation. So centripetal force is m v t squared over r, gravitational force m times g. M's will simplify. You can find at what maximum speed this car can go without leaving the track. That speed depends on two parameters. One of them is g. G cannot be changed on the earth if you are doing. The other one is r. Depend on how the curve is, sharp curve or not sharp curve, large curve. If it is sharp curve, you have to move slowly. The roller coaster car must move slowly. But if it is a large curve, big circle, in this case you can drive your car faster. So this is the last problem we solved. It was about roller coaster car in a circular path. The roller coaster car was moving in a vertical circle, so we calculated mass at that position. Tangential speed was given 20 meters per second. Fc was given. But in the second part, the question was about point B. At point B, what was the maximum speed of the car can have at point B for gravitational force of the car on the track? They said that this maximum speed occurs when Fn becomes 0. So when the car is in here, two forces acting in the car, which one of them is the Fg, always downward. Fn is acting perpendicular to the contact surface, which is going to go upward. This is the normal case when the car is moving with a speed, small speed. But if when the speed increases, so Fn is decreasing according to centripetal force equation. And finally, at maximum speed, Fn becomes 0. The only force acting on the car at maximum speed becomes Fg. That's why the question says that for gravitational force to hold the car on the track. And all the centripetal forces, gravitational force, and we solve this problem. Now we will continue with vertical circular path again, but this time roller coaster car will turn not from outside, not over the track, under the track. This is one of the sectional question. A roller coaster moves to a vertical loop, again vertical circular path, at a constant speed and suspends its passenger upside down. When it says upside down, of course, position of the car must be top. And top is upside down. And this is the position which the car will be at this position. In what direction is the force that causes the coaster and passenger to move in a circle? Yani, this is in fact asking you, what is the direction of the centripetal force? Because the definition of the centripetal force is the force that causes an object to move in a circular path. And we know that centripetal force is always towards the center of the circular path. And this is the circular path. So the roller coaster car follows. So the center of the circle is in here. That's why the force acting on the roller coaster car and passenger at that position must be towards the center, which means it must be downward direction. So, in what direction is the force that causes passenger and coaster to move? It is going to be downward, is the answer. Okay. Then, second part is about the force. What forces provides this centripetal force? Yeah, you are going to define the forces at that position. Which forces act on the passenger and the car? Absolutely, gravitational force acts. You can never remove gravitational force. One force is the force of gravity acting passengers at this position, which is going to be down to the ground. But as this car is moving, of course this car's wheel is in contact with the track. But track is this time above. So the car is pushing the truck upward direction, which is action. The track will be giving reaction on the car, downward direction, which is reaction. And the force on the truck is car is going to be downward direction. So this is the surface instantaneously horizontal. Of course, action-reaction pairs in this case must be vertical. So this is action on the track, which is the car is pushing the truck as it is moving. Then track is pushing the car down, which is downward. Yani Fm. Fm, normal force by the track on the car. So both are now pointing the center of the circle. Center of the circle. So if forces are pointing center of the circle, they are all positive. So to calculate the center of the force at that position, what should we do? We are going to calculate the result. Yani I will add Fn and Fg, which will give us the centripetal force. Okay, this is normal. The answer of this what force provides this force? Force of gravity and normal force by the track. But in here also we can maybe go much more. What is it? If I write Fn equation, Fn, I can write it like this. Fn is going to be Fc minus Fg. We know Fg cannot, am I right? Did I write it correct? Fc minus Fg, that's correct. Fn is equal to Fc minus Fg. Fc is greater than Fg to get an Fn. Yani Fc must be greater than Fg to get an Fn. But as speed decreases, which is v square over r, as speed decreases, what happens to Fc? Decreases. Then finally, Fc becomes equal to Fg. In this case, Fn becomes 0. What happened? As this time speed decreases, Fn becomes 0. But in the previous problem, when the car is over the track, at what speed Fn becomes 0? When it was maximum. Yeah, when the car is over the track, in this example, at maximum speed, Fn was 0. But if the car is turning not over the track, below the track, this time Fn becomes 0 at which speed? Minimum speed. Yani at some minimum speed car can follow the track. If your speed is less than that, car will fall from the track. It's going to be a crash. So maybe this is extra. So when the roller coaster car is over the track, above the track, FM becomes 0 at maximum speed. If the speed is greater than that, the car cannot follow circles. But if the car is below the track, FM becomes 0 not at maximum speed, at the minimum speed. If speed is less than that minimum speed, this time car will not again follow the circular track. Okay, we finished the vertical circle problems. Now we will continue with horizontal circle or path problems. One of the chapter question. 13,500 Newton car traveling at 50 km per hour rounds a curve of radius 200 meters. Find the centripetal dilation of the car. This is the section 1. Section 2, sorry. We should convert kilometer per hour to meter per second. And after that, you are going to write its linear, its value in years. You are going to use V square over R, and you will find AC. This is section 2. But our concern is now part B, about the section 2. Find the minimum coefficient of static friction between the tires and the road that will allow the car to round the curve safely. Yeah, and this car will move in a horizontal circular path which is flat. To keep this car on the horizontal circle, what minimum µs is required between the tires and the road? Okay, now when the car is making a turn, such a turn, now if you want to understand the case, we have to draw the forces first. What force is acting on the car? Fg is acting downwards, which is always downwards. Because contact surface is horizontal, Fn is going to be vertical. Because contact surface is horizontal, static friction force always parallel to contact surface. It should be this way or that way, depending on in which direction of tendency, in which direction car tend to skid. It tends to skid away from the center. That's why static friction force must be towards the center. When we check these three problems, these three forces, we see that two of them ineffective, which cannot be centripetal force. What are they? One of them is Fg, because it's perpendicular to radius. The other one is Fm, also perpendicular to radius. Yani, these two forces ineffective, they cannot be part of the centripetal force. Ineffective. But we need an effective force. So which force is effective? Along the radius. Which one is along the radius? Which force is along the radius? Static friction force. That's why in horizontal contact surface problem, yani when it says flat in the questions, we should directly give the answer. What force keeps this object in a circular path? You are going to say static friction force. Then I am going to write it. Centripetal force in this problem is static friction force. Yani Fc is equal to Fs. Okay, let's write the equation. What is Fc equation? M times AC. What is Fs equation? S times Fn. Now, I know that in vertical, this car is in equilibrium. In section chapter 2, we learn what is equilibrium. Net force on the car must be equal to 0 because car is not moving in vertical. To do that, Fn and Fg must be equal in magnitude. Now, instead of Fn, I can write Fg, which is M times G. Then I will continue. MAC is equal to µs mg. So M's will simplify. Then I get the equation for µs. µs is equal to AC divided by G. And remember, I said that this is correct for all types of flat surface problems. If an object is on a flat surface turning in a circular path, so µs is equal to AC over G. And now we can calculate it. Because I know how much is AC. In part A, we calculated AC 0.97. 0.97. G is 9.81. I think the result is going to be 0.1 almost. This is the coefficient of minimum value, the coefficient of static friction. If static friction is less than that, the car will start skidding. It cannot make a turn. If it is greater than that, much better. But minimum value must be 0.1. Less than that is not providing the car circular motion.
Teacher, Fn and Fg are equal to each other because it's equilibrium in vertical surface?
Yes, in vertical the car is not moving. In vertical. If an object is at rest, we learned in chapter 2. So this is condition for translational and rotational equilibrium. Alright, so this is the one of the problem. And I also had already here, US with AC over G. All is correct with an object moving in a horizontal circle and in contact with horizontal contact surface, yani flat surface. This problem is also similar to that one. 2,000 kilogram car rounds a circular turnover radius 20 meter. If the road is flat, keywords. If road is flat, so horizontal contact surface, μs is equal to AC over G. So coefficient of static friction between the tires and the road. This time μs is given. Calculate how fast the car can go without speeding. Yani VT. Translation is without tangential speed in a circular path. How fast car can go, which is not sometimes called, not in Europe, but safe speed. Yani maximum speed that car can have. More than that is not possible. Again, I will use this because I know that inside AC there is VT. If an object is a circular path. So I am going to write this equation for AC. AC is equal to μs times G. Then write AC by μl and by VT because VT is the question. So AC is equal to VT squared over R, which is μs times G. Cross product. VT squared is going to be μs RG. And also this equation tells you that this safe speed depends on which factors. Safe speed, and how quickly the car can go, or maximum speed the car can have, depends on in fact 3 things. One of them is μs, the other one is R, the other one is G. G is on the Earth everywhere almost the same. That's why G can, in comparison, we don't use G. Maybe in different planets we can compare the G, but on the Earth. So μs and R determines how quickly you can drive a car. μs and R. It says that if μs is greater, what does greater μs mean? It is the dry surface, dry, rough surface. In this case, you can make μs big, big μs, you can drive faster. But if it is a slippery surface, like rainy surface, right now it starts raining, or snowy surface, or icy surface, μs is going to be small. Small μs requires small speed to round the curve safely. Another one is R. What is R? R is the radius of the circle. If it's a sharp turn, which means small r, requires small speed to make safe turn. But if it is not a so sharp turn, large turn in radius and size, you can drive your car faster in this case. Okay, then my purpose is now to get the VT. Let's get the root. After taking the root, equation for safe speed is going to be μs RG. Then we will insert given into the equation and we will find how much is that speed. VT is going to be maximum speed. 11.7. μs was how much? Open 7. R is how much? R 20. 9.81 is the G. And result is going to be, VT is 11.7 meters per second. This is the maximum speed this car can have. If speed of the car is greater than that, slightly greater than that, this car will start skidding on the road and it's not going to follow circular path. It will tend to follow straight line path. Okay. This is another horizontal contact surface, horizontal circle question. Identify the forces that maintain circular motion of the following. A bicycle moving around flat circular. Again, keyword is flat. If an object is in contact with a flat surface, absolutely, 2 forces are ineffective. Ft is ineffective because perpendicular to radius. Fn is effective perpendicular to radius, but static friction force is parallel to contact surface, it's only effective force. So static friction force between the tires and the road provides circular motion of the bicycle. Okay, this is one of them. But A side talks about cyclist. In B, we are going to count the forces acting on the bicycle. Bicycle is in contact with the road. That's why I should count the force between the road and the bicycle. One of them was Fn, but it was ineffective. The other one is Fs, yes it was. Another force, of course, gravitational force, but it was also ineffective. When I was talking about a cyclist, yani the rider, then I am going to ask you a question. This rider is in contact with what? This rider is not in contact with the road. He's in contact with the bike. So I have to count forces between bike and the cyclist. And cyclist and bike are in contact at 3 points. One of them is seat. Second one is handlebars you're holding. Third one is pedals. When this cyclist and the bicycle are in contact from these 3 points, then forces must be acting from these 3 points. What are those forces? We said that every contact surface has 2 forces, absolutely. Fn and friction. So this friction force and normal force acting on the cyclist body will provide circular motion. And that's why answer is given. The force that seats, handlebars, pedals exert on the cyclist, yes. What are those forces? Friction force and normal force acting on the cyclist body. But as cyclists are making a round turn, general cyclist making his body incline. When it makes his body incline, these 2 forces becomes inclined. If the forces are inclined, this time we need to resolve the force into components. One component is going to be vertical, the other one is going to be horizontal. Horizontal one is going to be effective, vertical one is not going to be effective. Yeah, and that's why if you want to go more advanced in this question, these forces provides centripetal force, but which component of these forces? Horizontal component of these forces pointing in the center of the circular path is providing circular motion. One more thing. Sometimes you ask a teacher, in here also it says flat circular track. Flat circular track. But this flat circular track is not talking about cyclists in fact. It's talking about the bicycle. Bicycle is on the flat circular track. Cyclist surface is not flat, it's inclined. It's inclined. Now, be careful about this. If it says bicycle, yes, it is moving a flat road. Cyclist is not flat, it is inclined, its body, and that's why we have to think about the force between the cyclist and the bike. Cyclist is not in contact with the road. We should be careful about this. Okay? Sham, is okay? I hope so. If not, then take a note. And last one, a problem. In a popular amusement park ride, a cylinder of radius 2 meters set in rotation at an angular speed of 580 per second as shown in the figure. Figure is given. So the floor then drops away when the rider is suspended against the wall in vertical position. What minimum coefficient of friction between the rider's flooring and the wall of the cylinder is needed to keep the rider from slipping? As I said, we saw the video of the lesson, remember? The children were still suspended on the wall of the cylinder. Okay, I choose one of the child. Child's body is in contact with the wall of the cylinder, in contact. So there is action, reaction. Action is on the wall of the cylinder, reaction is on the child's body. This Fn is reaction force acting on the child's body. And we know reaction force is always perpendicular to contact surface. In here, contact surface is vertical, that's why Fn must be in horizontal. But child's body stays suspended. So now, there are 2 more forces acting on the child's body. One of them is gravitational force, which is acting downwards. But if only gravitational force acts, it's going to be sliding down. So, to provide sliding, to stop sliding, static friction force must be upward direction. You know, static friction force is also parallel to contact surface. There are 2 options, you can go down or up, but it is in the opposite direction of tangents of the skid. In which direction it tends to skid, static friction force is going to be opposite direction. So then, static friction force blocks gravitational force and keeps the rider at rest, in vertical. Now, there are 2 different motions in fact in here. There are 2 different cases. One case, this rider is in circular motion. That's why we have to say that Fn is the centripetal force providing circular motion. Then I'm going to say that Fn is centripetal force Fn is equal to m times AC. This is one case. But there is one more case. Chapter 2 is start study. This child is in equilibrium in vertical. If in equilibrium, that's right. Net force acting on this child must be equal to 0. Second fact is this. Now we go with second fact. Object stays suspended, so Fs and Fg must be in opposite direction, equal magnitude, so their sum is going to be 0. And to make this, magnitude must be equal. And Fs must be equal to Fg. I write the equation, Fs equation us times Fn, Fg equation m times g. Then I'm going to combine these two facts. Which facts? Circular motion, centripetal force, and suspended case. These Fn's are the same. I am going to insert Fn into that equation to get the final equation. Insert that. It's going to be Fn is m times AC. M's will simplify. When you write mu s, you will get the mu s equation. This mu s equation G over AC. It's the flip version of flat surface. I mean, vertical contact surface, G over AC. Horizontal contact surface, C over AC. AC over G. Now we can calculate mu s. G is 9.81. AC, you know, in terms of radius and omega, we can find it. And omega squared. So write that 3 times 5 squared, 9.81 divided by that number, we will get the result as 4.13. And if steady friction force between the child's clothing and the wall of the cylinder is 0.13 minimum, it will stay. But if it is less than that, yes, it will start sliding down. Okay. So then one more question. This question is about the bobsled example. Identify the force that makes a circular motion of the following. Bobsled turning corner on its track. Turning a corner, then bobsled making a turn on a corner. You know, this is the bobsled. When it's normal case, it moves in a flat surface. But while it's making a turn, it doesn't move on the flat surface. It's climbing the wall. The contact surface between the bobsled and the track is vertical. If the contact surface is vertical, normal force is going to be in horizontal. Also, we said that for circular motion on a vertical contact surface, which force is the centripetal force? Normal force by the wall. Yeah, the track provides a normal force. What about Fg? In effect, there is a knife and blade under the bobsled. This blade also making trace on the ice and it produces a force upward direction. This is also ineffective. Only effective forces, and that's why bobsled example, it was a mystery question, which force provides centripetal force for bobsled while it's making a turner? It's going to be force applied by the track, vertical side of the track. And we are going to finish this title with inertia and circular motion. We know that if net force acting on an object is equal to 0, object tendency is to stay at rest or to follow straight line path. This is known as law of inertia. Yani, as long as the net force acting on the object is 0, object will tend to move in a straight line path. But if you attach this object to a rope and make it moving, rope will counteract this tendency and cause it to follow circular path. So the perpendicular force acting on this object, perpendicular to what? Directional motion, directional velocity, is known as centripetal force, and they providing the circular motion. And as long as this perpendicular force to the tangential velocity is provided, this object will follow circular path. But if you cut the string, if the string broke on, in this case, object will not follow circular path. It was the quiz question. So, if centripetal force vanishes, like this example, so the object will start following not circular path. It tends to follow straight line path. And after that, depending on the environment, if it is a gravity environment, makes parabolic path. But if you do this for in space, because there is no at the force, it will follow follow straight line. About this, there is an example. When this object is moving a vertical circular path, if you break the streak, always tendency of the object is to follow or to leave the circle tangent. You will draw a tangent line, this tangent line. It will live this way. It cannot follow circular path anymore. It goes this way up, and after that it comes down. But if string is broken at the top of the circular path, again it will tend to follow the circle tangent to the circle. It will leave. But after it leaves tangent to the circle, then what kind of path will it follow depends on, again, surrounding things, environment. If it is no gravity environment, so there will be no net force, that's why object will tend to follow straight line path. But if it is a gravity environment like Earth, it will follow parallel projectile. Okay. And rotational motion of an object. And it's about a car example. Remember, if a car moves, makes sharp right turn, sharp left turn, what happens? Why the person just move towards the door? It was about this. Remember, we said them. There are two types of turns we can make. One of them is the sharp turn, the other one is soft turn. Let's first study soft turn case. And soft turn, this is a large circle with great radius. If it's a soft turn, in this case, the force acting on the car is going to be static friction from between the road and the car. But what about the passenger? Passenger is also in a flat surface. Seat is flat. But this time, we should count the force acting on the passenger's body. Passenger's body, the force acting on his body is the Fg, which is ineffective. Fm also ineffective because vertical, but Fs horizontal. Again, static friction force between the passenger's body and car seat provides centripetal force, makes the passenger move in a certain path. It's a soft turn. But when the turn becomes not that soft, sudden turn, sharp turn, in this case, this static friction force cannot be enough because centripetal force equation mv squared over r. If you make sharp turn, r decreases. If r decreases, centripetal force should increase. But what if you don't provide enough centripetal force? In this case, object cannot follow, this passenger cannot follow circular path. So what is tendency of the passenger? To follow straight line path. So then we will say that if friction force between the passenger and this seat is not sufficient, yani sharp turn, passenger, because of inertia, moves along original straight line path that way. Passenger moves that way, but the car makes the turn. Car makes the left turn this way. What happened? The passenger was on the left initially, then it becomes on the. What does it mean? Passenger is sliding from left to right. It slides from left to right. Then slides from left to right, and finally hits the wall. So passenger's body comes in contact with the wall. In this case, what will happen? A second force will appear on the passenger's body, which is the normal force applied by the wall. The wall is vertical. This force should be horizontal. Then, two forces will be acting on the passenger's body in this case. Static friction force between the seat and the passenger, and a fan by the wall of the car. So then, it will be enough keeping in the circular path. Okay. Alright, and last item is about universal law of gravitation in this section. In the past, people or scientists thought that center of the universe is not Sun, Earth. Earth is the center of the universe, was the center of the universe, and all other planets, stars, revolving around Earth. Until some discover of the telescope, they make some observations and then they get the data. This is not correct. One of the scientists, astronomer who made a proposal that this is not correct, Johannes Kepler, he said after the observation he realized that this is not fact. The planets, including the Earth, revolving around Sun. So planets are revolving around Sun in elliptical paths. Ellipse is a bulge circle. Ellipse is the center, yes. But if In one side its radius is short, in other side its radius is longer. This is an ellipse. And planets are orbiting the sun in an ellipse. This is the path followed by a planet, which can be Earth, Mars, Jupiter, Saturn. But where is the sun? Is it at the center? No. Sun is located in the focus. What is focus? It's a point between the center and vertex, somewhere here. There are two foci, focus, one on the left, the other one on the right. Sun must be in here or in that one of the focus. Sun must be located. And scientists continue to believe that Earth was the center of the solar system until Isaac Newton writes in an equation for these elliptical paths. What is this equation? This equation is talking about if an object is more elliptical path or circular path, we know that there must be a force acting on this object, keeping these planets in the circular path. So which force could it be? Isaac Newton answered that this force is gravitational force. Yeah, the force that keeps these planets around the sun is gravitational force. And this force is a non-contact force, a field force. It always exists between two masses and also always attract each other. And it exists between the large masses like Earth, Sun, and Moon, also exists between small masses like two desks in the classroom. And the force between Earth, Sun, and Moon is great compared to desks because gravitational force is inversely proportional to multiplication of the masses. I think I skipped that part. So gravitational force is directly proportional to multiplication of masses. Directly proportional. Yeah, if one of the masses doubles, gravitational force also doubles. If both are doubled, increased by 4, which was the quiz question, I think. Okay. So one fact is this, gravitational force is directly proportional to multiplication product of the object's masses. Second fact, separation between the objects are important. How far these two objects from each other, which is distance between them, also a factor. The gravitational force is inversely proportional to the square of the separation between the bodies. So, I will take separate distance from center of one mass until center of the another one, and so gravitational force is inversely proportional to square of distance, 1/r square. Inversely proportional means the quantity must be in the denominator. As distance increases, force decreases. As distance decreases, force increases. This question talks about that. Okay, and this equation, or this case, when the gravitational force changes inversely proportional to square root of the separation, is known as inverse square law. In mathematics, a quantity changes by inversely proportional to square root of the distance. That equation is known as inverse square law. Gravitational force universal gravity is an inverse square law because it changes by inversely proportional to square root of the separation and square root of the distance. Gravitational force is inversely proportional to square root of the distance. Ft is inversely proportional to r squared, but directly proportional to 1/r squared. And 1/r squared is called what? It's called inverse square root of separation. That's why we will write it. Gravitational force is directly proportional to 1/r squared, inverse square root of separation. These two statements are equivalent. Gravitational force is inversely proportional to square root of the separation, or gravitational force is directly proportional to inverse square root of the separation. In your statement, there must be only one inverse. One inverse. I'm sure I'll cite it like this. Gravitational force is inversely proportional to inverse square root of the separation. Inverse of the inverse would be direct. So it would be wrong. Okay. And this is the question. So we are going to combine these two facts. Which facts? Gravitational force is directly proportional to product of the object mass and 1 times m2. And 1 times m2 must be in numerator. Inversely proportional to r squared must be in the denominator. So now when we insert a constant, we write the equation. This is the equation for universal gravitational force. G capital M1 M2 divided by r squared. G called universal gravitational constant or constant of universal gravitation. Its value is 6.67 times 10 to the power negative 11. Its unit is also in this equation, Newton times meter squared per kilogram squared. We can write this unit by rewriting the equation for G. So we have to transfer our 1 times m2 divided by r squared other side by flipping. So it's going to be fg times r squared divided by m1 times m2 is capital G. So then I can get the its unit. Force is Newton, r is meter squared, m1 is kilogram, m2 is kilogram, kilogram times kilogram. This is how we get the units of such quantities. And last one is free fall acceleration. What is free fall acceleration? 9.81, everyone knows. What does this 9.81 mean? Because sometimes you confuse the force and acceleration. Force is attraction between two objects. Two objects attract each other. But this G, free fall acceleration, is when you drop an object, how quickly this object falls increases the speed. It's about that. 9.81 for the Earth. This 9.81 meter per second says that when you drop an object, this object on this Earth increases speed every 1 second 9.81 meter per second. Next second 1 more 9.81. Then 1 more 9.81. So we are going to calculate G on the surface of any planet. Earth, Moon, Mars. But to derive this equation, I am going to use the fact, one fact. What was the fact? When you're standing up on the surface of the Earth, this is you, a force acts on your body. We can write this to force act on my body by two ways. One of them is universal law of gravity. The other one is Newton's second law. Both are expressing the same force impact. They're equivalent. From these two cases, maybe that's why you students get confused. Yes, to get small g, I am using force. But it doesn't mean that g is force. So I am going to make them equal because both are calculating same force. That's why I can write mathematically they are equal to each other. When I make them equal, this m will simplify. What is m? M is my mass. My mass is not important for g. Your mass is not important for G, or this mass is not important for G. G, only mass important is planet's mass. Planet's mass must be the equation. Now, that's why free fall acceleration equation will have only single mass, not two masses. This single mass is going to be only planet's mass. One of them is this: planet's mass is important, but not only planet's mass. Also, its radius is important. Radius from the center to the surface. But if you are going to calculate G on the surface, you can write this. What about a G if you are going to write in the sky? You have to take the distance from center to that point. And that's why I wrote this. It is the distance from center of the planet until the point which you are looking for calculating this free fall acceleration. So then G, free fall acceleration depends on proportional to mass of the planet, but inverse proportional square distance from the center of the planet. Okay, and this is one of the chapter question. Comment on the statement. There is no gravity in outer space. What does it mean? Because when outer space, talking about that, you are moving far, far, far away from Earth. That's why R becomes such a big number, which results in gravitational field strength to be smallest number. Am I right, Sham?
Yes.
Good. And with this, we are going to finish. Which of the following is correct interpretation for AG is equal to capital G mass of Earth divided by radius of the Earth square? In fact, this is the free fall acceleration equation. But this free fall acceleration can be expressed by three different ways. One of them is gravitational field strength. Other one is free fall acceleration. Third one is acceleration of gravity. All are equal. Acceleration of gravity. Yeah, no, in fact, these three are talking about the same thing. A says gravitational field strength changes with the object's distance from the object. If I want to test gravitational position at my location, I should take distance from Earth to my position. This is correct. Yeah, right. In inverse proportional to square root of r. This is correct. Free fall acceleration changes with the object's distance from the Earth. Same statement, only different. These are defined differently. Description is different. Third one, free fall acceleration or acceleration of gravity or gravitational field strength independent of the falling object's mass.
Yes.
Is correct. My mass doesn't important for free fall acceleration. Because every object falls with the same G in the 11th grade, you learned that. What we carry is the planet's mass. Independent of the falling object's mass, correct? But dependent on planet's mass is also going to be correct. So then all of the above are correct interpretation is the answer. With this, we finished section 3 revision lesson. Next lesson, inshallah, we will start chapter review questions of chapter 1. Not all of them. Some questions, many important questions we solved during the lesson. Some questions we are going to solve.